Hey guys, want to talk about magnetism today, and this is kind of the third video in this unit. So here's a couple things that I thought you'd like to know about with the magnetism. First up, I got a little video here with hey guys, magnets. I wanted to show you a little thing that happens here. This is pretty interesting. When you take a magnet and you push it into a coil of wire, then you induce a current. Check it out. I am moving the magnet, and see how it makes the electrons in the wire, the charges in the wire move, and it's also making that moving charge is electricity. I'm making electricity there just by pushing the magnet in and out. If I go fast, I get a lot of current. If I go really slow, I get a small amount of current. This is actually where almost all of the electricity in this world comes from. The exception would be solar power. But there's usually a hydroelectric plant or a coal plant or something. When they open up the valve on Lake Murray and water starts to flow, then that turns a magnet, which makes the current go over here, and the makes electricity, and they send it out to us. So that's we are inducing a current there, and so we call this induction. Okay, so induction again can happen lots of different ways, but a current is produced if a conductor is moved in a magnetic field. If you just took a single piece of wire and moved it in a magnetic field, you would get a current across there. If you fly an airplane across the magnetic field lines of the earth, you get an induced current or induced voltage between the two ends of the wingtips. If I move a magnet near a wire, or a coil of wire especially, because each loop produces that much, and if I had 10 loops, then I'd have 10 times as much there. Or a magnetic field could change near a conductor or a coil. That would do it as well. I got a couple rules here for you. For a straight conductor moving perpendicularly to a magnetic field, the induced EMF, the electromotive force or the voltage, it's a better name for it, would be equal to BLV. B is the strength of the magnetic field, L would be the length of the wire that's moving, the conductor, and V would be the velocity. The faster you move it, the more voltage you get. All right, here's the rule for loops. If I have a magnet moving in a coil, or a magnet moving near a coil, or a coil moving near a magnet, or doesn't really matter which one's moving and which one's stationary, I get a voltage off of that. We saw it with the little demo, and the needle dashed back and forth. But the voltage would be equal to the number of coils times the change in magnetic flux per time. Okay, the flux is simply the strength of the magnetic field times the cross-sectional area of the coil. So right here, that coil has a certain area. If we somehow were to make that bigger or smaller, that would change the area, and that change in area over time would induce a voltage. Maybe I'm rotating the coil, and that's presenting a different face to the magnetic field. Maybe I'm rotating the magnet, and so magnetic field lines are sweeping. That would change my B instead of my A. But anytime I change any of those factors, I'm going to get a voltage induced here, and that would make a current flow, makes electricity like we did. Now, there is this negative sign right here. Like everything else in physics, a negative sign indicates direction. So that's just a thing to say you got to go the other direction. And we call this Lenz's law. Basically here, an induced current is always in the direction so that its own magnetic field opposes the effect that created it. It's a directional thing, so we don't have to worry too much about it. But let's say, for example, that I push that magnet into the coil. I'm moving it to the right. I move the magnet to the right into the coil. The coil is going to generate a magnetic field. When the current is induced in that wire, the resulting magnetic field will oppose that incoming magnet. And so those two magnetic fields will try to cancel each other out. All right, that's a little bit weird. But if I wanted to know the direction here, when I push the north pole of the magnet in, the current would go up over the front and back down the back. I'd have to put my fingers in the direction of that current with my thumb opposing the motion of the magnet, and that negative sign just reminds us of that. All right. Let's talk a little bit about transformers. Hey, here's another little demo real quick. Got a battery hooked up here, a DC power source hooked up to a coil, and you can see those electrons just running around, a lot of current there. That's generating a magnetic field, isn't it? I can see the direction of the magnetic field. If I move this coil around, see how the magnetic field changes to match that. Right here, I could put my fingers in the direction of the current. Now remember, those are the electrons that are moving, so they're actually negative charges, and the current goes the opposite direction. So I've got my fingers pointed into the board and back up a little bit, and my thumb points that red direction of the using the right hand rule there. But nothing's happening over here unless I bring this thing up close, and then I get just a little wiggle there on the voltage meter. If I had a light bulb in there, I'd be making a little bit of electricity there when I move this thing around. That would be like moving a magnet in and out of that, right? And the faster I do it, the more it moves and stuff. But I have to have a changing magnetic field to make this happen. Remember when we had the coil? As long as I'm moving the magnet, I get electricity, but if I just park the magnet in there, nothing really happens. All right? So this is the same thing. The trick is not to use a battery, but to use an AC power source like this. And here, as that electricity goes positive, negative, it alternates. So this is AC. That's making electricity over here. And, you know, getting it closer makes that effect a little bit closer and everything. So that's nice. In practice, we'd probably want to build these right up close to each other so that all the magnetic field lines go through the second thing. But absent that, the other thing that we could change would be the number of loops. Let me go back to the meter there. If I have fewer loops, then I'm catching less. Each loop is making a little bit of magnetic field, but not that much. And I'm going to put it up close here just to make it go. As I increase the number of loops that are catching the magnetic field, see how that increases the voltage? On the other hand, if I increase the number of loops in the over here, then you know, as I do that, that changes what's happening there. As that ratio of this number of loops to that number of loops determines how much electricity I get right there. This is called a transformer. We use transformers to turn one voltage into another, one voltage AC into a different one over here. So that's kind of a handy thing to do. We're going to talk a little bit about that. Okay, so here is a transformer. This is the usual symbol that you see here. You'll have some number of loops here and some number of loops here. This is where that AC power source is supplying power to these loops, and then over here I'm getting a different voltage over there. We call this side the primary. The primary of the transformer is where electricity is being fed into it, and it's generating a magnetic field over here. That alternating current would go, if I put my fingers into the board on the right and then into the board on the left, see how my thumb has to change directions? So there's that changing magnetic field. And just kind of let your thumb go up and down, up and down. That magnetic field will get conducted through that iron core of the transformer, and it holds on to all those magnetic field lines, carries them into the secondary. Onto the secondary side. This would be the primary of the transformer. This is the secondary. And right here I've got something like 1, 2, 3, 4, 5, 6 loops. And over here I've got something like 3 loops. So that ratio of 6 to 3 determines how much electricity I get out of this thing. A transformer in practice usually looks something like that. It's a little boxy thing with a bunch of wires wound up here, and you've got some wires that come off to make all those connections to the AC power and to the to your phone charger, whatever this is running. Okay, but here's what you need to know about it formula-wise. N1 is the number of turns on the primary side. N2 is the number of turns on the secondary side. So N1 would be 6, N2 is 3. And when I put 6 over 3, then that tells me what's going to happen with the voltage and also with the current. And in practice, you can use any two parts of that, any two fractions of that you want. if I have, if I go from 6 to 3, that cuts my number of loops in half. So right here, 6 over 3, the voltage on side 1 would have to get to voltage 2 there. On the other hand, my voltage goes down, the power has to stay the same. Okay, I'm not going to make more power than I started with. I'm not going to end up with less power. The power's got to be the same, and power is current times voltage. So you can see if you cross multiply right here, V1I1, it's got to be equal to V2I2. The power has got to be the same on both sides, other than what we lose through heat or vibration or anything like that. We're not worried about that. Okay, so that would be the rule that we need. In practice, they will give you 3 of the 4 numbers here, or maybe 2 of these and 1 of these, and ask for the other one. Kind of cover up whichever fraction you don't need. They'll give you 3 out of the 4 numbers, and you can work with the 4th one there. I don't think I can write on this screen here. No, it's not going to let me do that. That would be a real good place. It might actually. Hang on. Nope. All right. So I'll have to come back and do one of these for you a little bit later on. But basically put N1 in, put N2 in, put V1, and you could solve for V2. There's nothing hard about it. All right. Right here we talk a little bit about self-induction. I don't know that this is as important as transformers and inductance and all that, but think about this with me. If I change the current in that coil that you see right there, that will cause a change in the magnetic field, and any kind of change in magnetic field would induce a current. So I get a self-induced current or voltage here, and this is the way to calculate how much that comes up to. The voltage would be equal to negative L over delta I over delta T. L is the inductance of this thing, and there's a number that measures how much inductance it has, how good of an inductor it is. And then I could put in here that change of current per time, and that would give me a thing. If it's a solenoid, I can calculate the inductance down here. It's that coefficient about the magnetic fields, the permeability of vacuum or free space or whatever. N would be the number of loops, square that. A is the cross-sectional area of the coil, and then divide by the length of the coil. All right, so again, we're kind of taking the number of turns per length, how tightly wound those are. But that's the self-inductance there. That's kind of weird. I don't know that I'd ask a whole lot about that. If you had more than one inductor, you could add them. You'll remember that we added resistors in series and parallel. We added capacitors in series and parallel. Well, now we can add inductors in series and parallel. And look at this. If I put 2 or more inductors in series, all I have to do is add them. Whereas if I'm adding inductors in parallel, where if I have 2 or 3 or 4 or 15 of them side by side, I've got to do that flippy thing. Okay, this is the same way that resistors added. So just add inductors the same way that you add resistors. If I have an inductor followed by another inductor, the total inductance would be the sum of those two. If I have 2 side by side, parallel to each other, then I've got to put in the first one inverse plus second one inverse equals inverse. Remember the little trick on the calculator to make that work. So just remember that inductors work exactly like resistors, and that capacitors are backwards from that. An inductor stores energy in the form of a magnetic field, and right here the work or the energy that that inductor has is equal to 1/2 the inductance times the current squared. That's nice. I talk about time constants in current. We did this with capacitors. We can also do it with inductors. So the amount of current at any time in an inductor would be equal to the maximum current times 1 minus e to the negative t over tau. There's that time constant again. We have to calculate the time constant just a little bit differently. This time it's the inductance divided by the resistance. But when I feed my numbers into that exponential, then I've got everything I need. Just like with capacitors, you got to calculate tau. You got a way to do that. You got to calculate the maximum current, and you just use Ohm's law for that. Figure out what the voltage that you have on the circuit and divide by the resistance, and that would give you the maximum current, as if the inductor wasn't even there. When that circuit is closed and the current begins to go through there, it will get to the inductor, and it will start through the inductor, but now it's going through a coil. So that's a current in a magnetic field. It will generate a magnetic field from that current, but that changing magnetic field in the coil will self-induce a back current and cancel some of that out. So it's going to creep up like the capacitor charged. It's going to have that same kind of exponential growth to a maximum that you see right there. You probably know that there's direct and alternating current. Direct current is always the same. If you have a 9-volt battery and you graph the voltage, it would always be 9 volts until the battery died. Down here I've got a wall outlet, and it's putting out 110, 120 volts, but that is alternating back and forth. It's positive, negative, switching back and forth like that. Generators are used to generate electricity. And here you can see the poles of a battery. One side is north and the other south. And if I have this coil and I manually turn that coil, I physically turn the coil, then that's going to change how many magnetic field lines go through the coil. It will induce a current there. And the only difference between these two really is that this is a DC generator. And you can see that the little split ring commutator there would be connected to these wires. So let's say this is the north pole of the magnet, and this is the south pole. So my magnetic field is going to the left there, and my as it cuts through that coil, as it turns over, it's going to induce a current that comes out this side over here. And then when the thing turns a little bit farther, you can see that this split ring commutator switches sides. So the half of the ring that was here would come over here to this side, and now my loop has turned over, so it's still going to push current out this way, and it just keeps pushing current out this side. Every half turn I get a little pulse, and so I get boop, 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 and I get all these positive charges. That's not quite DC. We could smooth that off. We could use some capacitors and resistors and chop the top of this off and dump it down in there and smooth that line out if we wanted to. But that's getting close to a DC current right there, or DC voltage. On the other hand, if it's built with these split rings or slip rings like this, and I have little carbon brushes that touch each one of them, and that thing turns around, I always, the current is going to go, when the coil is like you see it there, it will come out one side, let's say this one, and then I turn it over 180 degrees, and the other line's going to be on the top, so it would come out this side. So the current comes here, and then it comes here, and then it goes there, and then it goes there. That makes the needle go back and forth, positive, negative, and you'd get a graph like that. All right, this one over here, it's always coming out on this brush right here, so I get a pulse and a pulse and a pulse, and it's always positive. All right, whereas this one's alternating, AC, going back and forth. A generator and a motor are pretty much the same thing. If I move the coil, I get electricity out. That would be a generator. In your car, you have a generator, and there's a belt where the gasoline engine of your car turns the belt, and that turns a generator. And so I'd be physically moving the coil in that magnetic field, and I get electricity out. That electricity goes and recharges the battery of your car so that it doesn't die. On the other hand, if I have an electric motor, I'm putting electricity into it, and that makes this whole thing spin. You could take a motor and make a generator out of it, or a generator and motor, just by instead of putting electricity in, you put motion in, and you get the electricity out. So those are kind of interesting to think about and pretty important in today's society. But that's enough for today. Thank you, and have a good day.